Alright, guys. We're doing homework today. Or homework. I finally finished Discrete, like the counting chapter. So now I'm doing now I'm on statistics, whatever, probability, discrete probability. So yeah. Let me put some music. Some music-y. Let's see. Yeah, okay. Alright. So I left off on this one. I think I'm getting the hang of this. Counting the playing cards. So yeah. Let's see. I got coffee too, as usual. Some coffee. Alright. Wait, also... Alright. I just wanted to see... I'm gonna write this down on the computer. So do this to myself. Okay. Oh my god. Okay, so one thing that I keep messing up is I calculate this incorrectly. Alright, I forget to use complement to calculate it instead of trying to do it manually. Because if this is at least one club, that means you can have one club, 2, 3, 4, or 5 clubs. 1 to 5 clubs. And I thought that you could calculate that by making a string where the first one would be guaranteed to be a club, and then the other 4 could be just the rest. And this was my calculation for that logic, because if you know the first one is going to be a club, all you have to do is choose the rank, and there's 13 ranks, so you just put there's 13 options for the first thing, and then for the 4 other cards you can just choose any card. So we already picked the first one, so there you started with 52 cards, now there's 51, and we're picking 4 of them, so 51 choose 4. But this is just wrong apparently, because I think the problem is that I don't know, like somehow these are not equal. These are just not equal. So, because I was looking at it, wait. Well, I can just look at this. Oh my god. So yeah, they say how to do that here. So this is no clubs is 39.5, which is there, and then you subtract that from the total hands that are possible. Right, is that correct? Yeah. So then the number of cards that contain at least one club is this number. Okay. I think I have to do this properly. Like I really gotta think about these questions, bro. Cause alright, if they say at least one club, right, that turns into 1 club, or 2 clubs, or 3 clubs, or 4 clubs, or 5 clubs. That's what that means. So to do this calculate, okay, so this is what I think I have to do. Every time I see a statement that says like at least or at most or whatever, I think I always want to reduce it to a statement of pure like this, where it only includes or and not as well. So this has at least, which is not that. So yeah, because if I had this, I would know how to in principle calculate this. This is the union of all these sets right here. So you would calculate each of these individually, and then you union all of them. You know, find how to calculate that, like the size of this entire thing. And that would be kind of annoying because there's like 5 different things here, and you'd have to use a weird intersection thing, right? So you could do that, or you could do the complement. So I'll say A is this, complement A, at most 0 clubs. So that's the complement. The complement is the reverse, you just not the thing. So yeah, so at least 1 would turn into at most 0, and that's complement. And this is easier to calculate. So if you have at most 0 clubs, that just means you have 0 clubs. Like so, you could just say that. Say. Yeah, 0 clubs. And this is pretty straightforward to calculate. They already have it here. It's 39 choose 5, but the reasoning for that, let me see. Yeah, so how many clubs? You just remove all the clubs from your selection, basically. So you're still choosing from all the cards, but you're removing all the clubs from your choice. So there's 13 clubs. So yeah, 52 minus 13 is 39, and that's 0 clubs. And now we can do this. So at least 1 club equals U minus the complement. And then we could paste in these thingies, and then this would be this would be this. Okay. All right. Okay. So let's try this again. So let's put this here, and let's find the complement, because I see there's at least, and I don't want to do that. So this is at most 0 clubs and at most 0 spades. Right. So yeah, this is pretty straightforward. So this is De Morgan's law. So when you have an OR, when you put the not in front of an OR thing like this, it goes to the first one and the second one, and you flip the OR to an and that's good. So flipping this one, we've already seen at least 1 clubs. The reverse is at most 0 clubs. So let's just say 0 clubs and 0 spades. So that's that. So let's set this up. Set that up. Alright, let's calculate this one. So if we have 0 clubs and 0 spades, that means we are choosing all the cards similar to last time, except we're gonna remove from our selection all the club cards and all the spade cards. So that would be 52 minus 13 times 2. Okay. So that's 26, choose 5. Yeah. So that's that. There we go. So, wow, okay. That was pretty simple. I was trying to build it. I was trying to do this without using complement, and that did not. It was really hard. So, yeah. Okay. So the probability, they're asking for the probability. So the probability of an observation, all observations, is 1 over this. Okay, so this is an event. So this is an event, and this is the size of the event, so how many observations are in the event. So the probability of the event is simply this. Alright. I'm gonna calculate that just to make sure we are good. Just to make sure. Always gotta check your work. Okay, so I got 97%. That kind of makes sense. Okay, they used this. Let's see if we get the same answer. Yeah, okay, I got the same answer. Okay, that's good. Okay, so I really need to memorize that. So, yeah, I want to make sure to memorize that. So if we say at least, sometimes it's easier to work with the complement. So yeah, I really gotta pay attention with that. Alright, let's try this one. Okay, so an online vendor requires that customers select a password that is a sequence of uppercase letters, lowercase letters, and digits. So all the possibilities is 26 plus 10. to an nth power. So a valid password must be at least 10 characters long, and it must contain at least one character from each of the 3 sets. Okay, so the restriction. At least 10 characters long. Okay, let's just... At least 10 characters long. And at least one character from... At least one... uppercase, and at least one lowercase, and at least one digit. And at least one lowercase, and at least one digit. Okay. This is our event, let's say. Okay, so with probability that a selected string with exactly 10 characters results in a valid password. So a valid password must be at least 10 digits long, so 10 digits and greater. Okay, and they're saying what is the probability that a random selects a string with exactly 10 characters? So it has exactly 10 characters and these other requirements. And they're saying the alphabet for the strings in the sample space from which the string is drawn is the union of the 3 sets of characters. Wait, so the alphabet for the strings in the sample space is the union of the 3 sets of characters. Is this the sample space? I think. I think that's the sample space. Okay, because there's 10 characters and this many choices per character. It's just the alphabet, the union with no restrictions. So yeah, that makes sense. Okay. So we know it's gonna be 10 characters. Okay. Bro, it is so cold. Alright, I'll BRB. Okay. I put on pants and a hat because it's so cold in here, bruh. So goddamn cold in here. The fan is right above my table, so it's just freezing. There. Okay, Okay, so I can take that out because we're assumed to have 10 characters. Okay, so how do I approach this? So let's try the complement. Let's try the complement. So if I real quick. Is there is this correct? I'm just trying to figure out, like, okay, whatever, let me start typing. So the opposite of at least one uppercase means no uppercase, 0 uppercase, or 0 lowercase, or 0 digits. Is this a correct opposite of this? I think so. Alright, so this is this might be easier to work with. I'm not sure. Let's keep going. So if we have, how do we calculate this? This is the union of these. So let's just try this out. So 0 uppercase just means you're using lowercase for the digits. Right. Okay. Alright, so here's what we're gonna do. So no uppercase means we remove the uppercase possibilities, and we just use lowercase or digits. Alright, 0 lowercase is the same thing, and 0 digits is this. Because we have uppercase, lowercase, uppercase digit, lowercase digit. Okay. So now that we did that, let's find the intersections. Let's give these thing. Okay. Let's give these a thing. So it's A plus B plus C minus AB minus AC minus BC minus plus ABC. And these represent the intersection of those A and B, A intersect B, A intersect C, intersection ABC. So yeah, I don't really know. So if I have the intersection of these, it means 0 uppercase and 0 lowercase, so only digits. Let's set that here. So okay, let's keep on track with this. So AB means only digits, AC means only AC means only lowercase, and BC means only uppercase, and ABC is just 0, because if you have 0 of everything, you just left with nothing. So it's, yeah, it's just okay. So let's put these down. Yeah. So this is gonna be fun. So okay, this. Let's just say 2 times this and that. And then this. And then we gotta add this plus this times 2. It's not plus, it's minus. There I go with the typos, bro. Get out of here with the typos. Alright, so yeah, this is 2, this is A and B. This is C, adding. This is the intersections, paired intersections. And this one is 0. Okay. So that's complement. Apparently. Let's just double make sure this is complement, because I think last time I tried doing something like this, that really messed me up. Like I was accidentally thought something was a complement when it really wasn't. It was just not. So at least 1 uppercase. The opposite is at most 0 uppercase. And yeah, pretty sure that's right. Let's just continue. So yeah, I can do this could be no. Let's just pick that. So that's that. Alright, so now the probability of E happening is just E over sample space, right? And E is this. So okay, so that's oh my god, what is this? Dude. This is getting out of hand. Look at this. I'm not typing all that. I'm not going to type all that. What I'm going to do instead is store these as variables on the calculator, and then and then do it. So the sample space is this. I put that into X, and then the complement is this. Okay. This might take a second. Okay, so I typed it. Let's see if I typed it right. So I got negative 2 times 26 to the 10th. It's negative 10 to the 10th. 26 plus 26 to the 10th. Positive 2 times 26 plus 10 to the 10th. Okay. So I'm doing x minus y over x, and I got 81%. Is that correct? This is looking there. They have different numbers here, like 62. That's kind of concerning. But let's see what they do here. Okay, so I got 1 minus 2 times 36 divided by 62 to the 10th power minus 52, 62 to the 10th plus 2 times 26 divided by 62 plus 10 over 62 to the 10th. Yeah, got the same number. Alright, that's cool that we did this correctly. Alright. I think a critical part for this was just recognizing the complement, because yeah, I usually struggle with that. Alright. Let's continue. Let's do this. Conditional probability. Nah, JK. Alright, I'm gonna do this some ratio as usual. We've reached... Oh, they added more servers. Growth. Siege. This is what I wanted. Oh my god, what is this? It's lagging. This is so funny. Okay, who's on the leaderboard? 57 million. Oh my god, this dude. Whatever, bro. Don't do it. Don't do it, alright? So this is Siege. This isn't Arms Race. Maybe we should do Constructor. Let's do it. This is so funny. Alright. This has to be just so laggy. Like, jeez. Oh my god. Yo, that guy is huge. Oh my god, who is... He's so... I can't even... I can't even see the whole... Oh my god. He's covering the whole screen. Dude, he's like covering like the whole screen, dude. He's so big. Dude, I'm pretty sure he's gonna get big enough that he's just gonna end up getting stuck in a wall or something. can I even get any kills? Because I'm on such a low level compared to all these people. Maybe he's dialing it down a little so we can get some XP. Oh my god. Oh, I actually got some XP. This is crazy. Oh my god, dude. The boss is... Okay, yeah, I'm gonna use lower resolution because... Jesus. Oh my god. This is what happens when you do growth siege. I knew this was gonna happen. I remember a while ago I wanted to play Growth Siege. And here it is. Did I get what I wanted? Who knows? Dude, that guy is so big. He can't even move. This is so funny. Dude, there's so many of them just disappearing because of... Oh, wait. Oh, whoops. Thanks for healing me, dude. I almost died there. Oh my god. That guy's playing on Xbox Series X. Dude, you can see his tank like shaking because of how big it is, colliding with everything. Yeah. Soon he's just gonna end up teleporting off the map or something. Like, I don't know. Like, he's bound to just... Look at this. Now, he's... Blood is vibrating. 58 million? Jesus. That is so funny. Oh, what the... Just close my own music. Alright, I think I'm gonna take off the names and the scores. Just because of... He's been shaking since 45 million. That is funny. That is truly funny. This is where real fun comes in. All right, like just stupid stuff like this. Oh my god! Don't push up. Oh my god! What is that? Jesus! I was gonna say Jesus. This is so funny. Oh, what happened to my comment? Can I move? It's lagging so bad. It's... Wow, whoa. It's lagging, like it's super delayed. Oh my god. It is super laggy. What is this? 35? Okay, it's back. That guy said he got disconnected. That's crazy. Oh my god, those are giant circles. Dude, that is hilarious. Little girl spazzing out. Over gay lag? US Central. Eat your potatoes. Dude, this is so funny. What is this? Is just crazy. Who's a nail gun? Nail gun, bro, is like 1 million. Oh my goodness. Oh. Nah, there's no way I'm gonna get any kills with this. What's my score? Bro, I barely got a score. What I think I should do is get the nail gun, because I cannot reach at all. Like, the constructor is not it. Oh my god. This is crazy. They are literally, they're right on top. Safe spot? He said it's safe right there? I do not trust that. Oh! Safe spot, bro. Yeah, right. Look at this. It I mean... They might... Oh my god. This is just so funny. What is going on? Oh, the penta. There's a penta. Maybe I should be a penta. 40 seconds of no lag. Alright, I'm gonna choose my tank. Because there's no way I'm getting any XP as a constructor. I gotta like change my tanks, bro. This is so crazy. Alright, let's do penta. Max bullet speed. Oh my god, dude. This is next level, bruh. Oh, there's so many. It's lagging. It's lagging so hard. Oh my goodness. Activate lag. My Chromebook? Dude is using Chromebook. No, he's not gonna make it. That Chromebook, it's over. Oh my goodness, that's a lot. I'm just looking at the minimap. It's colorful. I've never seen so many colored dots on the minimap. That is crazy. Can I get some XP though? There's so many annihilators. Oh, there goes the timer. Oh my god, bro. Okay, like, this is fun, but I gotta grind, bro. I literally gotta grind. I gots to grind, bro. Gotta learn new things, expand my knowledge. Alright. That was crazy. That was good. Alright. Okay. So conditional probability. So what's up with this thing? Jesus. Right. Dude, I'm still cold. I gotta change my jacket or something. I don't know. Dude, I'm still cold. I need a freaking, like, I really need a blanket or something, dude. What is this? Hold up, hold up. Alright, I'm back. Okay. So yeah, Okay. So I'm doing dish. I got like an hour left. Alright, let's see. Okay. Bro, I gotta learn this. This is what I would need to learn, bro. Cause I was trying to read some research papers and I couldn't understand what any of it was or read any of the math proofs because I didn't know about conditional probability and stuff, so I'll be trying to learn this. But yeah, anyways. So, let's say, so there's a blue die and a red die. The event is that the two numbers sum to at least 11. So there's the event. So the probability is 3 over 36. So suppose the experiment starts by rolling the blue die first. And the blue die comes up to be a 5. So that means that it could only be 5 out of 6, right? Okay, it says the information. The sample space has shrunk from the set of all 36 to the set of outcomes for 5 thing. And then the probabilities need to be adjusted. Okay. So that's interesting. What? So it's telling you that the experiment and outcome is when you roll 2 dice. But they're telling you the information that the first die is a 5. So it's like partial outcome or something. That's kind of weird. It's like partial outcome. What? So to say the sample space has shrunken? So is that what that means? Oh yeah. So E is the sum is at least 11. F is that the blue die is a 5. Oh. So they're saying if F so this is to consider 2 events happening. And then like the new probability. Okay. Alright. So it's the intersection, the probability of the intersection divided by the probability of the conditional event thing, the given event. Okay. So finding the probability is this if the distribution is uniform. And then it just turns into this. Yeah, I know that. Me knows. Okay, so here's a more. Abstract example. Okay. So let's see. So this is the sample space. It's uniform. And this is the event F, which includes these outcomes. And the probability of this happening is adding up all these probabilities. 1/13 times 5. Alright, I guess. Is that what it is? 5? That's not right, right? 5/13? Hell no. Oh, given. So they're calculating the given thing. So probability of A given F is, for example, 0. A given F. Oh, that's so true. So they're saying given that F is an event that is happening, or whatever. I guess that does shrink the sample space, because initially, isn't everything a conditional probability? But it's like assumed that the sample space is, like, if you don't include conditional, it just assumes that it's the sample space. It's conditioned on the entire sample space. Isn't that what I've been doing? I think so. Anyways, because yeah, if we said, for example, the probability of A given the event that anything could happen, that's like the entire sample space, and that would be just 1/13, because yeah. But here they're saying we're not looking at the whole sample space, we're looking at just F. And is A in F? If it isn't, then the intersection will be 0, right? And then the probability just turns into 0. So all these outside of F do not intersect with F. So all the probabilities would be 0 on that condition. If you do that. So all these in here though are in F. So there's 5 of them. They're saying probability of each outcome is 1/13. Yeah. So event F. Why is this? Is that something that happens? Oh, cause here it's F over the sample space. That's the probability of all of F happening. So F includes 5 thingies. So the probability of F happening, given the sample space. Let me see that. Let me see that. Let me write that down. So the probability of F happening given the sample space. Can I say that? That would be the intersection over the sample space. Okay, so there's 13 items. So the probability of the intersection divided by the entire thing. Well, the probability of the sample space happening is 1, because that's all of your stuff here. That's like saying the probability of the sample space given the sample space, which is 1. Okay. Alright, whatever. I'm gonna just continue. I'm not gonna get too deep into it. So let's check anyways. No, let's go back. So F, I know it's 1/5 because it's like there's 5 items in F, but is that true? I mean, is that true? Probability of F intersecting S is, this is, wait, this is, F is a subset of S, so we don't even have to include that they intersect, because F intersect S is still just F, doesn't change. So yeah, F it's a subset. Okay, so F has 5 items in it. What? So wasn't it 5/13? Is the probability of F. Is not what it is. Bro, I gotta piss, bro. Alright, I'm back. Let's see. I'm just gonna work through this example and see if it makes sense. So yeah, the sample space. Did I run out of lead? I think I just ran out of graphite. Oh, never mind. Thought I did. Yeah. So sample space is blue dice is rolled and a red dice is rolled. So 6 times 6. Alright. Which is 36. Okay. 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 That's our sample space. Right. And they're saying there's an event E, which is a subset of the sample space, and it equals the 2 numbers on the dice sum to at least 11. Yeah.
So, okay, 5, 6, 6, 5, and 6, 6. Yeah, and then so the size of that is 3.
Okay. And the probability of E
is 3 over 36. Right? Is that how that goes? Can I say probability of E given the sample space? Can I say that? Yeah. So, anyways, the probability of E is cardinality of E over cardinality of sample space. Okay. Which is 1 over 12. Okay. Let's say we have event F, which contains just one thingy.
5, 6.
Nah, F is that it starts with a 5. So that's what that equals. Cardinality of F is 6. Okay. Because the second choice, you can only have 6 numbers. So probability so let's say the probability of E happening given that F happened. Right. So we would get their intersection bye given that F happens. Okay. So the probability of F equals 6 over 36, 1 over 6. And the probability of the intersection is you just get the intersection and find the probability. So what is that? What's the intersection? So the intersection, so we have these 3. So the intersection is going to be 3 or under. The first one on F is a 5. So the intersection only has one thing in it. So
1 over 6? Is it 1 over 6? No. 3 over 5. Wait, this is a different one. Oh yeah, it is 1 over 6. Okay, cool. Very cool. So let's... Okay. This is pretty straightforward, I guess. You just have sets, discrete sets, and then you figure out the probabilities. And the conditional is just a different formula. You just do the intersection. Okay. Alright, let's see. So right here. So a fair coin is flipped 3 times. That is a single outcome. Is our thing. So the sample space is 2 to the 3. Yeah. So 2 to 3 is the sample space. So let's just say it's the string oops. It's the string heads it's this set to the 3rd power. Okay. And it says W is the event that there are at least 2 heads. Alright, here we go. So W is at least 2 H. I could count it manually because there's only 8. The sample space is 8, so I don't really you know, whatever. So it says at least 2 heads. At least 2 heads. Another thing you could say is at most 1 tails as well. At most 1 tail. So 0 tails or 1 tails. I think I want to do that instead. So I'm going to do the at most 1 tails. So how many of those? Isn't this like 6 or something? Or 4? I don't know, bro. At least 2 heads. I'm just going to write it down. I'm just gonna write it down. So let's see. Yeah, this is just 4. Because if it had 0 tails, there's only 1 possibility. If it had 1 tail, there would be 3 possibilities, so it's 4. So yeah, right. 4. Cool. So F equals first flip is heads. So it's heads blank blank. Okay, so the size of that is 2 squared, which is 4.
Right.
So, what is the size of the intersection?
The intersection is 3. Because 3 of them motherfucking start with heads. So, yeah. Okay. Okay, what is the probability of F given W? Is it 3 over 4? Cool. That was pretty straightforward. Oh my god, no. Not the cards. The cards. This is how you know it's bad. They're giving you the probabilities before, so you got more work to do. Given the probability. Nah, JK. But anyways, so he's saying, suppose that a player sees the first 2 cards, and those 2 cards are the Ace of Clubs and Ace of Diamonds. So the first 2 are a pair. So they say, what is the likelihood after seeing the first 2 cards that the hand will have 2 pairs? So we shrink the sample space, get the intersection, and do some stuff. But let's get more paper. More paper. Let's choose this spot. So okay. So the total sample space is 52, choose 5. A equals all the strings where the first 2 cards is Ace of Clover and Ace of Diamonds. Yeah. Let's put that Ace of Clover and Ace of Diamonds, and then the rest here is that. Okay, and then P is the strings that the hand has 2 pairs. Because they say here, what is the likelihood after seeing the first 2 cards that the hand will have 2 pairs? So 2 pairs. Let's get that probability. So, alright, let's see. I've done this before. I remember. So I think what we do is well, actually, hold up. What's the size of A? Isn't it something choose 3? 52 minus 2 choose 3? 50 choose 3? Because we chose the first 2 already. Okay. So we have 13, choose 2. Because we get 2 different ranks. And then in there we do 4, choose 2, squared. And then the last one, the last card, can't be from the, well, let's see. There's 11 ranks left to choose from. So, do we do times 11? Right, times 11. 11 ranks to choose from. Should I do that or choose from all the cards? I would get 44, right? 11 times 4. I don't know. Let's see. So anyways, so we chose 4 card. Well, wait. So there's 2 ranks we can't choose from. So, wait, what? Isn't there 13 ranks? And each one has 4 cards. So, we have removed. Yeah, we have 44 cards left. But yeah, so it's just 44. Okay, so that's that. That's this. Okay, so what is the intersection of those? Let's find that out. So the intersection is that the first 2 is the aces or whatever. Okay. Okay. So the first 2 are known, so all we're doing is choosing the second pair. So there's 12 ranks to choose from. And we're choosing 2, so we're doing 4, choose 2. And I guess the last one is still times 44. Alright, so this one we choose from the 12 ranks, and then we do 4, choose 2 for the suits, choose 2 cards, and for the last card, there's only 44 cards left because we do 52 minus 4 times 2. Right, we got 2 ranks out. Okay. And they're asking the probability of pair given A, P given A. So that is the probability of intersect A over probability of A. Okay. So the probability of A. Damn, bruh. This is getting crazy. Alright. I think this is where we could plug this in. So we got the intersection. I think it's just this over A. Alright, so 12, 4 choose 2, 44 over 50 choose 3. Alright. I got 16. Oh! That's what I got. You thought, bruh. You thought. Alright, that took a little bit of time to do. So I had to find A, which is pretty easy. That was pretty quick. And then I had to find P, which was the pairs. And I think I took a little bit of time on that. And then the intersection took about equal time to figure that out. And the probability was a little quicker than finding the intersection. So I gotta work on the intersection thing. I gotta get that down packed. So yeah, like choose 2 ranks, and then for each of them you do just 2 of them. Choose 2 cards each, 4 cards, and the last one there's only 44 cards to choose from. Cool. What is that? So like times here, times 13 choose 2. Yeah, I don't know. I'm just gonna have that memorized. Oh no, not the compliments. God. Alright. So the probability of E and the probability of the complement sum to 1. Even when conditioned. Yeah, that makes... Okay, that makes sense. Dude, what? Are they proving it here? Nah, I'm good. Me good. Me good. Dude, I'm still cold. I'm still cold, dude. Alright. Alright. Let's see our time. We got a good 20 minutes left. We have made some progress. Yeah. Alright. Let's see. Okay, so we have stuff. Space for that. This is what happens when you don't write in order on the freaking on the notebook. Okay. Okay. So we have a blue dice and a red dice. So the sample space is 1, 2, 3, 4, 5, 6. And combine that with the same thing. Okay, this size is 36. And yeah, so they're saying something. So what is the probability that the sum is at least 10 given that the two die have the same number? Okay, let's say that. So let's find the set where the sum is at least 10. I don't know what to call that. I'll put sum greater or equal to 10. That is going to be starting with 5, 5, 5, 6, 6, 5, and 6, 6. Alright. That's right, right? 5, 5 is 10. 5, 6, 6, 5, and 6, 6. So that's that. The size of that is 4. Alright. So the size of that set is 4. Okay. So the probability that the sum is at least 10, given that the two die have the same number. So what's the set of that? I'll put num same, or nums, yeah, I don't know. Nums equal, EQ. Nums EQ. Yeah. So that's the set. We got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that's nums equal. The size of that is 6. Okay. Yeah. So what is the probability that the sum is at least 10, given that the two die of the same number? Okay. Okay, let's just write that down. So P of sum greater or equal to 10, given nums equal equals probability of nums equal on the bottom. On the top we have probability of the intersection. Okay. I can calculate that. So the intersection, let's see real quick, is 2. Okay. 2 over 6.
Which is 1 over 3. Nice.
Okay.
We have here probability that the sum is less than 10 given that the two die have the same number. So we can use a formula for this. They are complementing the first event, and then the second event is staying the same. And we know that when you add them together, they equal 1. So it's 1 minus this, which is 2 over 3. Okay. Okay, so what's the probability that the sum is at least 10, given that the blue die comes up to 2?
Okay. So I'll call that B2. Blue 2. I guess.
What is it?
So I'll mark here BR for this. So the first one, I'll say the first one is the blue die. Okay. So here I'm gonna say B2 equals 2, not set, and then the other one is that. So the size of that is 6. Alright. It's just 2 with every other number for the second one.
So they're saying, what is the probability that the sum is at least 10, given that the blue die comes up 2? So
let's write that. So okay, so sum greater than 10 given B2. We already know sum greater than 10, but we don't know the intersection. So let's find that out. So the intersection is 0, I think, because they're saying that the blue has to be 2, but in the sum being greater than 10, there is no blue equal to 2, so it equals 0. Alright, yeah. Very nice. Yeah, so this is the same as the other one. It's 1 minus this, because they are inverting the first one and keeping the second event the same. We need that this is the complement of this. This one was 0. This one is going to be 1 minus 0. Okay. Yeah. Okay. Let's write these down. So we have a blue and a red die are thrown. B is the event that the blue comes up at 3. Cool. So I'll just call that. So B is something. Let's just write down all of them. So it says it comes up at 3. Blue equals 3. So we have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. Okay. And E
is the event that the sum of the dice is 8. So that would be, for example, 4, 4, 3, 5, and 2, 6. And then the opposite. So 5, 3, and 6, 2. Okay. So they're saying, what is the intersection? 1. Because only one of these matches. And then the B is 1, 2. It's just 6. Okay. Yeah. Okay. Okay. This is good. This is good practice. Alright, let's do that. So B is a blue is an odd number. And then E is that the both dice come up odd. Right. I don't want to write down too many of these, but I think I have to, so. Cool. So the blue comes up in odd number. Okay. So it's gonna be 1, 3, 5 for the first one, and the second one is normal. Cool. So the size of B is 3 times 6, which is 18, right? Okay. B, that's B, and then E is that they both come up odd. Okay. Okay. And the size of that is 9. 3 times 3. Okay. So they want me to find the intersection. Right. So I think the intersection is just 9. I think it's just 9. Okay. So I think this is 9 over 18. Right? Yeah. Yeah. Okay. Okay. So when 2 dice are thrown, the event E that the 2 dice are the same is probability 1 over 6. Now suppose the probability of E is conditioned on the event F that the blue die comes at 5. So it'll be 5, 5. So it's be 1 over 6. Yeah. Wait, what? So conditioning on the event F did not change the probability of E. Is that true? Oh, it is true. Huh. That makes sense. So if F is a subset of E, then they're independent? Is that what that means? Is that what that means? This is weird. So I guess if I'm just thinking that if these two, bro, what? Alright, we're gonna see. We are going to see. Let's see. So, experiment. Pick a random permutation of ABC. So, sample space is just 3 factorial. Alright. 6. And let's say they say there's an event E where A comes before C. So C is always after A eventually. So here, yeah. Okay, and there's an event F where B is always first. Okay. And there's a probability for that. So the probability of their intersection is 1/6. So that means they are not independent, I'm guessing, because wait, what? Is that how that works? No, because you gotta multiply. You gotta multiply. Oh, they're independent. They are independent because this equals this times this intersection. Yeah. And the conditional would be if you did probability of this, and the conditional if you did probability of E, and then you added on condition of F, it wouldn't change anything. So that would mean they're independent. I like that better, but this, probably gotta memorize that too. So their intersections. So the probability of them individually equaling their intersection probability would mean they're independent as well, somehow. So they're independent. Yeah. Okay. So they're saying... So we still have this, where A comes before C. Now we have G, event G, which is where A comes before B. Okay, and then you're gonna find the intersection, right? 1 of 3. They are not independent, because when you find their intersection probability equals 1 over 3, and that is not these two multiplied. Okay, so alright, let's do this. This might be our last set of questions. We've already reached 2 hours, so I'm just gonna do this one last, and then yeah. Okay. More space. Where that space at? Where that space at? This is distracting. Alright. Okay. Alright. This is our last thing. So here we go. So we have sample space, always. So sample space is a fair coin flipped 3 times. So tails, heads, the third power. The size of that is 2 to the 3, 8. Okay. We have an event F, which is the first flip is heads. Alright. That should be 4, probably, but let's just write these down. So we have H, 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 T, H, and H, H, T, and H, T, T. Yeah. So that's 4. So I got 1 T and 2 T's, H. Okay. Alright, so yeah, size of that is 4. We have E, event E, which is the number of heads is even, including 0. Yeah. So we have 0 heads or 2 heads, and that's it. Cool. So T, 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 and that's for 0 heads, and then for the 2 heads, we have H, H, T, H, T, H, and T, H, H. And that's it. Okay, so that's 4 as well. Okay. And W is at least 2 of the 3 flips is heads. Yeah, so there's 2 heads or 3 heads.
So yeah, let's get 2 heads. Or 3 heads. Right. That's also 4. Okay. They're saying, what is the probability of F? That much. E is also that much. This is also that much. So it's saying, what is the probability that the first flip comes up heads? What are these again? First flip comes up heads, even. So this first, even, and whatever. So yeah, F intersect E. What is that? So it's 2. Okay. Yeah, so it's 2 over 8. Are they independent? Is F and E independent? I don't know, let's check. So, probability of F times probability of E. Let's find this out. I should write down the probabilities as well. So this is half. This is half. And the probability of this, the intersection is 1/4. So they are independent because when you multiply the probabilities individually with the probability of the intersection, they are the same. And this, I just know that. I did that. So yeah. So they're asking for first flip heads and yeah. So F intersects W. So the first flip is heads with W. So that's 3 of them. H, T, H, 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 H. Okay, the size of that is 3. And the probability is 3 over 8. And yeah, they're not independent, right? They're right. They're not independent. So yeah. Oh my god. Alright. Alright. So that was it, I guess. Should I continue? I don't know, bro. Nah, I'll call it. Alright, that was my homework. Thank you for watching. Have a nice day. Goodbye.